Okay, so I got a video request for the Wittig reaction, which in your textbook, if you're using Bruce, I think the 7th edition and the 2nd edition, it's page 827. And for my class, it's lesson 18. I think. All right. So anyway, first of all, we divide this up into 2 separate steps. Let me get a piece of paper out here to cover that up. I did a little too much pre-work here, more than I meant to do. So, of course, we're always thinking about this. First of all, what's the basic reaction? And then what's the mechanism? And as I've said many times before, sometimes it's easier to memorize the reaction and to think about the mechanism from that. And sometimes it's easier to memorize the mechanism and think about the reaction from that standpoint. I've given examples from that before, so let me not do that now, but let me first of all say that we're going to consider both of them, and then we're going to decide how's the way we want to memorize this. So the first thing is, and this is just in your book, you have a carbonyl-carbon. There's a carbonyl-carbon, carbonyl-oxygen. I'm sorry about the background noise. I can't do a whole lot about that right now. So a carbonyl-carbon, carbonyl-oxygen, and then another carbon double bond with a couple alkyl groups coming off. I've labeled them R and R prime right here so we can keep track of everything. Of course, they might be the same alkyl group. Shoot, they could be hydrogens, right? And that's we'll probe that in a little more depth later. But for now, we've got a couple things coming off there. All right. Now, by the way, why don't you consider? Please pause the video right here and name this compound. Pause it and name it. Okay. Supposing you paused it and named it. This is acetone. Okay. What's the name of this? Well, that's a complicated question. For we can't know because we don't know what the alkyls are here. But we are calling it an ylid. I admit, that's a Y. I admit that I typically will call this an ylid, and I don't know why I've fallen into that bad habit. So I call it an ylid in class. The proper name for this is an ylid. It's a phosphonium ylid. Okay? And so these two things come together, and they make this. So we've discussed before the different kinds of reactions and different categories of reactions. And if I were asking you what category of reaction this belonged in, what would you say? So remember that reaction number 1 was introducing functionality. I should have had this pre-written. Number 2 is eliminating functionality. 3, changing functionality. 4, making carbon-carbon bonds. 5, breaking carbon-carbon bonds. And 6, acid-base. Right? That's the 6 I suggest. Of course, you can divide these reactions up into any category, any number of categories that suits your purposes. But this sort of helps us organize everything. So if this is true, introducing functionality, eliminating functionality, changing functionality, making carbon, breaking, and acid base. What class does this reaction belong in? Pause. I'm going to ask you to pause the video here too. Pause it and tell me what class you believe that belongs in. Look at these again. Introducing, eliminating, changing, making, breaking, and acid base. Pause the video. Okay, supposing you've paused the video, I would argue that what we've just done is we've made carbon-carbon bonds. Now, you might say, well, we're changing functionality because we have a carbonyl-carbon here, right? Or a ketone. And here we have an alkene. And I would agree that that is definitely changing functionality. But the most unique thing about this is that we're making carbon-carbon bonds. And I'll justify in a little bit later here in the video why I think that's so important. Okay, now let's look at the mechanism. First of all, if you're in my class, I can tell you this mechanism is not going to be on the exam. Will it be on the ACS final? That's an open question. In order for you to answer that, you need to get an ACS study guide and look through there and decide for yourself if it's important enough. My recommendation is that you do not memorize this mechanism. So I go over it just because that's sort of a black box to a lot of students, and it's unsettling to not know it. So let's go over it. The book shows it. You can't handle it. It's not that hard. but again, okay. So I should have left these arrows off in the beginning. But suppose you start out with acetone or some carbonyl carbon, and you start out with phosphonium E-lid here. Now we're used to this by now. You are expecting every time you do a mechanism, your goal is to identify the target and identify the nucleophile. Okay, so when we're dealing with carbonyl carbons, by far and away, the most common target is going to be that carbonyl carbon right there, right? For two reasons. Number one, it's planar, and number two, it's electron poor. Beautiful target, all right? And then, of course, when that gets hit, this guy comes up here. So we're expecting that. Now, what's the nucleophile? Well, the very first nucleophile we did in Organic 1, I believe, well, besides acid-base reactions, was addition reactions with double bonds, right? So you have a pi bond here, and that is the nucleophile. I think that's kind of hard, frankly, because if we had a lone pair of electrons, it's real easy to see that those are the nucleophile. But this is the nucleophile here. So that goes here, and let's draw what happens if we get that. If we get that, I've got a carbon here, phosphorus. I'm going to draw my phenyl groups over here instead. My R prime, they haven't done anything, but I now have a new bond here, right? There's the new bond, and then I have a lone pair of electrons up there. That's a minus. Okay? Oops. I forgot. Sorry. We actually have, this phosphorus is electron poor also. Because it's a big atom, it can take extra electrons. So really that goes there. This is a mistake. Oops. That's a mistake. There's no minus on there. These actually go, boom, like that. Okay? And now that we have that, now I'm going to say, here's a good example of how, because I'm looking at this and going, I have no idea what to do next. Probably you're saying the same thing. You could memorize it, but I think there's something better here. I think if you memorize the reaction very carefully, the mechanism sort of falls out of that. So look at this. Here's the reaction. What must happen now? If this double bond becomes this double bond over here, what must happen? And this carbon, which was bonded to the phosphorus, is no longer bonded to the phosphorus. I think the only answer is that's got to go here, and this has got to go here. Okay? And that'll give it to us. Now, as I often do with mechanisms, I'm going to leave the atoms in the same orientation as they were when they started, so we can see what's going on. Right? And of course, we know that this thing doesn't take the shape, but at least I can keep track of everything, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay? R carbon R, R carbon R, R carbon R. Alright, and that's the mechanism. So obviously this is the same thing as boom, boom, R and R prime. So that's the mechanism. And there's a few questions we could ask ourselves about this that I'm not going to deal with in this video, but a couple questions obviously. First of all, can these be hydrogens? What are the restrictions on that? The mechanism is oftentimes going to help us with that, but I think the best thing to do for that, to answer that, is to look in the book and see what restrictions the book gives us. But walk through the mechanism. Having the mechanism helps you decide, can these be hydrogens? Here's another question. What happens, can this, and what happens if this is also asymmetric? So what happens if this is R double prime and this is R triple prime? Is this going to have two products? Is this stereospecific? And I think the mechanism we have in the paper is enough to answer that question for you. Okay? In other words, is this, let me write the question down, is this stereospecific? Right? Are we going to give rise to EZ isomerism? This is no question about it. That kind of question is ACS final material. So it's a good thing to think about. But the bare minimum is for you to be able to take a phosphonium E-lid and a carbonyl carbon and hook these guys together and recognize that what you're doing is you're making a carbon-carbon bond. So again, Bruce does this. I think all organic textbooks are going to do it like this. You see how I've kept everything. I've kept everything oriented the same way. If I cover those up with my hand, I can see basically this thing over here, right, where that carbon is bonded to that carbon over there. So when you're memorizing this reaction, my recommendation is that you set this out in such an orientation that it makes it easy for you to memorize. I think the final question I'm going to ask is, if these two give you this, the final question I'm going to ask you, and this is something that you know this is going to show up in a quiz or exam, tell me. So what? I said the final question. I've just thought of another really good one. Well, that's a phosphorus. Oops, sorry. C6H5, 3. What's this going to give you? Okay, that's a question you've got to be able to answer. Can you read my writing? You know what this is, right? It's triphenylphosphine, elid, right? Plus some ketone. I know my writing's messy here. So that's one question you've got to be ready to answer. Then another one that you've got to be ready to answer is, if I have this and this, how did I get there? Okay, be ready to answer those two questions for our conversation, which is forthcoming in class. Hope this video is helpful. Thank you for the request.